everybody. My name is James Powell, and I'll be your presenter for today's session. Today, we're going to talk about what is real in Python. We're going to talk about things like identity, snapshots and live views, hashability versus immutability, why immutability even comes up in our programs, and we're going to try to understand how we can use Python better in our work in order to accomplish specific goals, in order to debug problems that we may see in our code by understanding the basics better. This is even more Python basics for experts. For those of you who are joining us on our Discord channel, I want to encourage you to ask questions along the way. We'll be in the Discord channel watching out for questions and answering them as they come up. For those of you who may be watching this later on in recording format, of course, please do join our Discord server and ask any questions that come up as you try to apply all of what you see today to your work. We want to show you how Python and how more deliberate use of Python can have material improvements in the quality of the work that you do by starting with the basics and presenting them as though we are a team of experts. As I said, today we're going to look at 4 major topics that have a certain basic nature to them, but as we dig into them, we can see there's quite a lot of depth and quite a lot of very interesting information. We will, of course, look at identity versus equality. We'll look at snapshots versus live views. We'll look at hashability versus immutability, and we'll look at immutability versus mutability. With that said, I'll share my screen with you so that we can jump right in. What is the difference between equality and identity? And why should I care? Let's take a look. Well, the first thing that we need to understand when we're thinking about things like identity and equality in Python is that in Python, variables work slightly differently than we may be used to if we are C or C++ programmers. That is to say, in Python, variable names are just that. They're names. They are names that we can use to refer to some underlying data. They aren't themselves the memory locations where that data sits. They're really just a reference to that. And this is why we can have multiple references to the same underlying data. We can have multiple names that are bound to the same underlying entity. In Python, we have some operators that we may use to ask questions about the data to which a name refers. Now, I'm going to be a little bit imprecise in my terminology because it is a little bit too much for me to say every single time the object or the data to which a name refers. And so instead, I'll say something like the object that x's represents, the object that y's represents, or x's and y's. And I'll skip a little bit of the additional verbiage. Well, here in this code example, we can see there's x's, there's y's, and there's z's, or zs. And x's and y's contain the same values, but they are not the same piece of data. Z's isn't the same piece of data and doesn't even contain the same values. And our equality check here tells us that x's and y's, despite being 2 distinct pieces of data, happen to be equal. It kind of makes sense. They contain the same values. And z's doesn't happen to be equal to either of them. It is completely distinct. If we were to switch this from an equals check to an is check, we would see that x's and y's are not the same piece of data, and x's and z's definitely also not the same piece of data. We have these 2 operators, and they help us identify whether 2 pieces of data might be equivalent, they might be used for the same purposes, they may contain the same value, or identical. They are actually the exact same piece of data. There are some wide-ranging consequences to this. For example, if these 2 names refer to exactly the same piece of data, a mutation via one name will be visible on the other name. If we happen to have some structure like a dictionary, and we ask if 2 dictionaries are equivalent to each other, note that that equivalence only takes into account the contents of these dictionaries. So here I have D0, D1, and D2. Well, D0 and D1 are equivalent even though their entries are in different order. They're equivalent because they contain the same keys mapped to the same values. And of course, D2 is completely different than the rest. It is not equivalent to anything here. Again, if I swap this with an identity check, I'll see that D1 and D0 are completely distinct objects, and D0 and D2 are completely distinct objects, or to use the longer formulation, D0 refers to a distinct object than D1, D0 refers to a distinct object than D2. However, the object to which D0 refers is equivalent to the object to which D1 refers. Do note that when we're checking for equality, An equality check is something that can be customized and may be specific to the nature of the use case or the data that we're looking at. And so if we use an ordered dictionary and we ask if two ordered dictionaries with the same keys mapped to the same values are equivalent, the answer is no, unless they happen to be in the same order. And so that ordering criteria for equality on dictionaries is just part of the use case. For example, if we think about tree structured data or document structured data, like JSON data and XML data, it should be fairly clear that in the JSON standard, the order in which we see nodes is not considered to be a property of the underlying document. And so we want dictionary style equality, where if the nodes are in slightly different order, well, it's the same document as long as it has the same keys and the same values. Whereas in XML, the order of the nodes is a property that we may maintain. So with XML, we want the ordered dictionary style equality, where the nodes have to appear in the same order. We have to have the same keys mapped to the same value in the same order. Well, it turns out that we can actually customize what equality means for our given objects, and we may very well want to do this. However, we can never customize what identity means. The is check can never be customized. It is always the same operation. It is always identifying if two names refer to the same object. And as we'll see under the cover in C Python, that has a very precise meaning. There is no way for us to override that. There's no way for us to overload that. There's no way for us to customize that or implement that at all. However, for an object like this, here we have some names and some values and some metadata. We may very well want to say, you know what, don't consider the metadata for the purposes of equality. That's just some tagged metadata. When I loaded up this data, maybe I wanted to figure out what the provenance of it is, so I stored the file name that I read it from. But if I have two pieces of data with the same name and the same value, they're equivalent, even if the metadata doesn't match, even if they came from different sources, whatever the case may be in terms of what we're storing in this metadata. Because we can customize equality, that has certain implications. For example, when you do an equality check, you may be running custom code. And as a consequence, the equality check can really do anything it wants. It can return any response that it wants as long as it's a true or false value. And it doesn't necessarily need to take into account just the fields on the object. It could always return false, it could always return true, or it could do any arbitrary behavior that it wants in pure Python. Now, one important detail of the is check and one important detail of Python is when we have the equals or the colon equals syntax in Python, when we have the assignment or assignment statement or the assignment expression, that cannot be customized in any fashion. We can generally customize quite a bit of the Python vocabulary. We can implement the square bracket get item, the parentheses call, the dotted get attribute lookup. We can customize all of those. But one thing we cannot customize is the equals assignment. In other programming languages like C++, you can do these. You have things like copy constructors and move constructors. These do not exist in Python at all. X equals Y always means the exact same thing, irrespective of what custom code somebody has written. It always means X is an alternate name to refer to the same thing that Y refers to. And this is what we might call a name binding or a name rebinding if X previously referred to something else. There is one small caveat for this, however, and the caveat is making use of some mechanisms in the object-oriented model, specifically some mechanisms related to class construction, like prepare and swapping out what we're going to use as the namespace in which the body of a class will be implemented or will be constructed. What we can do is we can actually put a hook on the set item for the namespace, and we can actually trigger on this assignment and this assignment as well. And so if we look here at our output, we can see from our logging output that we in fact did trigger on this assignment and trigger on this assignment. So yes, sort of, we can maybe put a little bit of code behind that equal sign, but only in this very narrow case. And generally, we probably shouldn't do this for anything very meaningful. Maybe if we're going to do this, it should be something like maybe an optimization that's fairly transparent or some debugging purpose. We really shouldn't try to use this for anything too substantial. Now, if we want to check if two objects are identical, well, we can check if they're identical using our is check. We can say is xy, and we can see here no. And we can ask is z's x's? The answer is of course. That equality check, that assignment cannot be overridden. This always means that z's refers to the same object that x's refers to. Another way that we could identify if two objects or if two names refer to an identical object is by looking at their ID. the ID in Python gives us the unique identifier for a given object at a given point in time. So if we look at their ID values here, what we'll see is here, the ID of x's and the ID of z's match. In fact, if the IDs of two names match, that means that they refer to identically the same object. X's is z's is exactly the same thing as the ID of x's equals the ID of z's. And consequently, x's is not y's is the same thing as the ID of x's does not equal the ID of y's for a given point in time. Let me show you what I mean by that. There's a couple of qualifications for how we can use IDs, but before we look at that, let me show you an immediate consequence of two objects being identical. If two names refer to an identical object, what I'll say in shorthand as two objects being identical, what that means is a mutation that's visible on one or through one name or on one name is visible on the other. In other words, if x's and y's are independent, then if I change x's, y's won't change. But if x's and z's are identical, therefore they are not independent, a change that I perform on x's, a mutating change I perform on x's, will be visible on z's. And this is exactly what we see from this example. We can see that even though I did append on x's, z's also appears to have changed. Well, in fact, what x's.append does is it goes and it performs that mutating change on the object to which x's refers, which is the same object to which z's refers. This is the most immediate consequence of identity and equality. If two things are identical, you'll see that a change via one name will be visible on the other name, for better or worse. Whereas if they're merely equal, well, then they're just merely equal at some point in time. A change on one will not cascade over to the other. Now, do note that there are certain performance optimizations that have been added to Python that are largely inconsequential, but if you start looking at the idea of a bunch of things, they might leave you a little bit confused. For example, small numeric values and small strings in Python are interned. Because the major consequence that we can see from identity is if two things are identical, a mutation that occurs via one name will be visible via the other name. Well, if the underlying object is immutable, then there can be no mutation via either name. It's immutable by definition. Well, strings and numeric values are immutable. Therefore, what the Python interpreter will do is, upon startup, at least CPython, it will pre-allocate small, commonly seen numeric values, such as the number 0, the number 1, values that will show up in pretty much every program that we write. It will also allocate small strings only once. And so if we have the string ABC and the string ABC, there's a possibility that we are actually looking at the exact same string just through two different names, even if we've created this string in two different parts of our program. Here, we can see an example of that. If I create the numeric value 123 twice, you'll see I get the exact same ID even though I created these separately. Whereas if I create a larger numerical value like 1, 2, 3, 4, 5, 6 twice, you'll see, well, they were created separately. They occupy two different memory addresses. They're two distinct objects. However, because integer values are not mutable, there really is no consequence to whether they're the same or different. In fact, there's really nothing we can do with this property. Do note one very interesting detail of this example. I have to use eval here because if I don't use eval here, what I'm going to see is that all of the IDs are going to be the same, 4388 here and here, and 450 here and here. And the reason for that is Python will do constant folding. And so when I run this code as a script, Python will identify that certain constants will appear in multiple places in this code. And I'll say, you know what? I see this constant twice. Let me just fold it into one instance of that constant. That constant folding works because, of course, 1, 2, 3, 4, 5, 6 is an integer, which is immutable. And so here you'll see that it's just reusing those constants. If I perform the same example interactively at my read eval print loop, I'll see a different result. And so to get around that detail, what I'm going to do is add just a little bit of indirection. I'm going to force Python to try to reconstruct these numerical values live by going through eval. Now, one thing that I might see about constant folding is constant folding actually will occur basically within what we might call a compilation unit, within the unit of code that will be compiled when we build bytecode for Python, which is basically a module. And so if I have a function that is defined in one module, f, and another function in another module, g, and they both refer to the same values, the same immutable numerical values, and I have a function h that's in a different module that refers to the same values, well, I can dig deeper into these functions and look at the constants that they have that are stored. And what I'll see is that the constants that f has and the constants that g have, they're actually been folded. They're the same. Within that compilation unit, we're just going to reuse that same 1, 2, 3, 4, 5, 6, 7, 8, 9 value. However, across two different compilation units, between one module and another module, they'll be different. Again, there really are very minimal consequences unless you're digging through your Python interpreter to look at the ID of a bunch of things and you see the ID happens to be the same for small strings or small numbers, and you see some slightly different behavior at REPL versus in your scripts. There really isn't any material consequence to this, which is why they're so comfortable in allowing this optimization to reduce redundant memory allocations, to reduce memory use by not reallocating the same thing over and over and over again, even though you only need to allocate it once and then reuse it multiple times.
Thanks for watching. If you enjoyed this video, give it a like, hit subscribe, and check out the recommended video on the screen. See you in the next one.